times the derivative of the,
Yeah, let's get that.
the derivative.
I like that, Sydney, that's nice. So if we have an integral like this, and gamma is some curve, closed curve, whatever, it doesn't have to be. Let's say that gamma maps closed interval into the complex plane. Let's pretend we know something about gamma, that this is gamma of A right here. Jesus Christ, sorry. I'm having some trouble with my gammas. And then this is gamma B right here, so the orientation looks like that, or the flow. So Sydney, yeah, you're right on with this. This was integral A to B f of the parameterization
Yeah.
times gamma prime of t. Put a prime there, don't dot it, and then we got that.
Yeah.
Cool, so let's do that, just as a refresher on how to do that thing over there. I need a parameterization of the curve. So let's come over here, write up what we have, and help me out. Can someone give me a parameterization gamma?
Q to the IT.
E to the IT,
From 0 to 2 pi.
0 to 2 pi. What's the radius of this circle? What's the radius of this circle?
1.
So what do I need to do? I need to tweak it a little bit. How do I get a circle of radius r?
Multiplies by r.
Yeah.
Just like that, yeah. So now I got a circle of radius r. So this is my gamma. So I'm going to go to the definition Sydney gave us. We go 0 to 2 pi. 1 over, literally just plug in the parameterization. Then here we're going to have gamma prime with respect to t. Notice that gamma prime in I comes out front. That's it. Looks like we're spelling stuff. Right? So now we got r I e to the I t dt. Help me.
Everything but the I cancels.
Oh, I like it. Sydney's getting some good sleep. I like it.
Well, I wouldn't say all that.
Well, your brain's working quite well,
Yeah.
so.
Again, without any AC or heating.
Right on fumes.
And that's just 2 pi.
That's just 2 pi. I, right? And the I comes out front. So not too bad. We can do this. Take some complex ideas, literally and figuratively, and turn it into a real Calc 1 problem. What about this one? So now, instead of the circle being centered at 0, it's centered at W. And I've got Z minus W down here. Do you remember what we came up with there? It was also 2 pi I. And if you do the integral just like we did it, what's great is that the parameterization of gamma is W plus r e to the it. Notice how it's basically the same thing because the derivative of this with respect to t just brings the I out front. And then everything looks the same. When you put this z in here, it cancels the w out. It's the same integral in the end. Just really a change of variables. That's all. What do you think this means? Negative gamma. Going clockwise, yeah. So when we have a curve, gamma, if we talk about the opposite of that curve, this just means traverse backwards. So how do I do that integral knowing some things? Well, I want to have a few properties. And so we're going to use the book a little bit today, so you might want to get that ready, because I'm going to walk us through some stuff and talk us through some stuff that I don't want to write up on the board. So let's see, where are my properties? Well, where are our integral properties? Our curves. Should be like on page 73, 74 up. Ah, yes. Proposition 4.6 part B says that if you traverse the curve in reverse, it simply reverses the sign of the integral. So that minus can just come up here. And so this would be negative 2 pi in reverse. Just remember, counterclockwise is default. If you go clockwise, that changes all the results we're talking about. So, on the page 76, at the bottom, there's a definition that I don't want to write. It's the definition of antiderivative. So let's take a look down there and read through it together. If f is holomorphic in the region G, what does that mean?
Differentiable everywhere.
Differentiable everywhere, and same thing as analytic, right? So differentiable at every point and at a disk around that point as well. So it's like thick differentiability. And we know that f prime, the derivative of this holomorphic function, is little f for everything in that domain. Then big F, the thing we started with, is the antiderivative of little f on G, also known as the primitive of f on G. This is nothing new. It's just a lot more technical than we're used to looking at. An antiderivative is the thing whose derivative is the thing we started with. So just to refresh your memory, in case any of this seems remotely odd, if I had z cubed, the antiderivative of that would be what? Yep, power rule, right? So all your calc stuff is the same. For getting these antiderivatives, nothing will be different. You know this, you've done this a lot. So this is the function, this is the little f, this is the big F in that theorem. Or not even theorem, just a definition, but notice that they call this the primitive. So that's a new word. You don't get that one. That's a very complex analysis specific term. Primitive is antiderivative. How many antiderivatives are there for a particular function? I get a little f. How many of these primitives exist? One. One. Okay, more than one. One at least.
Infinite.
Infinite because the plus c.
Oh.
Right. Yeah. So like they shift up and down or left and right. In the complex plane, plus c can make you move up or down if you add an imaginary part, or left and right if you add a real part. Okay, cool. So they give us a nice example there, but we know this. They show us that sine of z is an antiderivative of cosine of z on the entire complex plane. And they use the definition. Notice how they proved that using the exponential definition, the one that Labina hated. Didn't you hate that? You tried to find it on the tangent problem. That's it. The one you deliberately eschewed. Okay, so let's take a look at theorem 411. I'm going to walk us through some things and just give some comments about them. Theorem 411 is where? Page 77. Awesome. Let me write up the result, the main part of it, and let's talk about what does it mean. So please read through the hypotheses. We've got a region. We've got a piecewise smooth path. That means that it's got some corners, but only a finite number of corners. And otherwise, it's smooth and differentiable in between those connecting places. So this is theorem 411. Piecewise smooth path. It's got this parameterization that could be very complicated, right? It could be piecewise to get each of the pieces. We don't know. Doesn't matter. If f is continuous, the little f is continuous on G. That's the assumption about the integrand here, continuous. And f, big F is any antiderivative, then this integral right here, this thing that can be computed like this, can be computed more simply like this. It's the antiderivative evaluated at the end minus the antiderivative evaluated at the start. So let me get a picture here to help you out. Here's gamma. This is gamma of A. This is gamma of B. And this is the antiderivative of little f. So big F is a primitive. What if I change the path? So I've got this path gamma. What if I had a path gamma 1 that looked like this? Piecewise. Does it change the value of the integral?
No.
Doesn't. What if the path goes? Different integral? No?
So
Yeah, go ahead, Noah.
it
Yeah.
can be curvy. It doesn't just have to be a straight line.
Correct. Yeah. It's not piecewise linear, it's piecewise smooth. So in between the pieces, we've just got a differentiable curve.
What's the most efficient curve?
This is most certainly not the most efficient. That would be most efficient. What's up? So yeah, talk.
But then it doesn't make sense with the circle thing then. If all things get us, if all paths should get us the same value, then a smaller circle, or then just subtracting the same value from itself if we have a circle that starts at one point and then finishes at that point, should just always be 0, but it's not.
Where's 0 in here?
The fact that you're
Okay. So hold on. So let's go to the hypotheses. This is great. So what are the hypotheses? The hypotheses are there exists an antiderivative on the region the curve lives in. Right? So we've got this region G. Let's go through the hypotheses here. G is an open connected region. It could have a hole in it. That's still a region, and it's connected and open. So let me make this a little bit more complicated. Gamma is a piecewise smooth curve in here. And you're like thinking about a curve like that, I think.
Sure.
If f is continuous on G, so now my integrand would have to be continuous on this whole space, which would be, and maybe G is just everything except the center. So that's cool, we could take that. There's G. And f is any antiderivative of little f. The problem here, Noah, is that we may or may not have this thing existing. So let's talk about the thing that's throwing off your intuition. It's that 2 pi I thing,
Yeah.
right? So let's look at that. So in the 2 pi I thing, and we haven't, this is going to show up in a couple theorems why this is the case, but I'll give it to you now because it's troubling you. So we have 1 over z. Let's just look at that in the simplest case. Over a circle, around 0, some radius. This function has no antiderivative on the whole plane. That's the problem. I can't find an f that is defined on everything except 0.
You couldn't just say the ln of z?
The problem with ln, remember how ln was defined? There's a big problem right here on this whole negative axis. We had to take that out.
Oh.
So natural log is actually only exists on everything except 0 and the negative real axis. So natural log isn't even continuous on
Right,
this.
it's the spiral.
Yeah, and let's think about like the principal natural log, if we were thinking about that, is the natural log of the absolute, of the magnitude, plus I arg of z. That's the principal arg. So when I come in this way, I'm getting a negative pi arg. When I'm coming in this way to the same point, I get a positive pi arg. So this function is not even continuous on that plane, but it's not differentiable on the region containing, a region containing the whole disk around 0, or the circle around 0. So
Okay.
that's why we're getting a different answer there. This would be true if I took this thing here and I took a curve gamma that stayed where this was all good. So like if my gamma did this, awesome. Then that result's gonna hold true. But this result won't hold for this function.
Alright.
Does it feel a little bit better?
Yeah.
And I'll give you the conditions on why that would be the case in just a few here.
Okay.
Good stuff. I appreciate your discomfort.
Thank you.
Yeah. It's educational discomfort. Great stuff. Let's see, so where were we? Where was I? 411. Thank you.
Small question.
Yes.
So when we're saying it's like small f of gamma and we're integrating it into big F of gamma.
Yes.
So it's practically like what we've been doing so far, right?
Yes.
So it's nothing new.
It's
Nothing new in terms of integration.
correct. Yes, ma'am. Let me give you an example though of how to use this. So let's give a nice solid example, and then this will like make Labina feel better, and maybe Noah continue to feel on the up and up about this. We'll see. But let's say let's go back to this guy right here, and let's say we got gamma here, and gamma is good old unit circle, our circle of radius r. So let's say that's IR, that's R right there, and gamma is just RE to the IT. So now we got a circle. I've got a function z cubed that is certainly continuous everywhere. It's like freaking holomorphic, and it has a derivative everywhere that we can easily demonstrate this is the case. So this is the antiderivative. This is my big F. This is my little f. This is my big F.
Z to the fourth.
Thanks. Indeed. Indeed. So I can take this curve at the start when t equals 0. So this is going to equal big F at gamma of 2 pi minus big F of gamma at 0. And you can see that this is going to be 0 because these are the same point.
Yeah.
But this would work even if I didn't have the whole circle, right? Like, let's just say I had that nice gamma right there. So I give you that, I give you that, and let's call this gamma 2 right here. So this integral over gamma 2 of z cubed dz. I don't have to go to the parameterization and turn this into an integral about t. I don't need to do that at all. I'm just going to say this is 1/4 z cubed to the 4th. Having trouble integrating today. Take the end point, which right here, what is the end point? Negative r. And the start point was positive r. And plug those in. So this is going to go from z equals negative r to z equals positive r.
And, oh no, they're the same.
And that turns out to be 0 also. But it's just that simple. It's just look at the endpoints. Don't worry about the path. Same integral if I did some crazy shit.
What? Yeah.
Ooh, yeah, it does. Ow, 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 ow.
I mean, the squid's mouth would not. If it's that's more like an octopus. Squid's mouth would be on the bottom.
Let her live. Oh, jeez.
It's true. They have a beak
You
in
don't gotta
between all
get
their tentacles.
scientific on us. Yes, exactly. Interesting.
You take a lot of shit.
It's fine. I can deal it out as much.
I was gonna say, he talks a lot of shit, Dr.
Yeah, it's cool. It's cool. I was like this too. I brought a lot of shit on myself throughout my life. By being outspoken, just speaking my mind.
Saying things and stuff.
So it doesn't matter what the path is. That's the awesome thing. With this method, the path does matter because we have to have the parameterization. So we moved away from the parameterization needs in certain circumstances. So let's take a look at then. Ooh, actually, let's just write the result up here. This is some result in the book, but I'm going to put it up here. This is probably some sort of corollary. So if we have an open connected region in the plane, we have a curve inside the plane. Notice, I like how they actually don't allow equality here because this is a curve and this is an open region. They could never be equal. This has no interior. This is all interior. So if F is continuous on, let's see, and F is continuous on G. That's an easy thing to verify. So I can take a look at this and say this is entire, in fact, right? Polynomials are entire. The derivative exists everywhere. So it's certainly continuous everywhere. So if F is continuous on G, then F has a derivative on G. You're going to like this, what's coming up here, Noah. F has a derivative on G. Notice the hypotheses are F is continuous on G and F has a derivative on G. Then the integral over that path, and I think that path is probably a closed, piecewise smooth closed path. Yep, should put that up here. So piecewise smooth, PWS, closed path. Then the integral is going to be 0. So if the function is continuous, if it has a derivative on G, then the integral around any closed path, which we can easily believe from what we've talked about, is 0. Why is this useful? It's not super useful because you'll see it instantly if you're going to go use them. You're like, oh, same start and end, just plug it in, 0. This is useful in the contrapositive form. What is the contrapositive of this statement? Yeah, so what does an and turn? As we negate this and statement, what does it become?
R.
So
Yeah, so not P and Q becomes what? Or not Q, right? That's a De Morgan's law. Just kind of remembering that stuff, right? So the contrapositive is, and this stuff right here, this is just like the universe we live in, so we're not going to negate that stuff. If, wait, so tell me, so that's the negation of that, but
Then that would not be equal to 0.
yeah, so here we have P implies Q. What is the contrapositive?
Q, not Q implies not P.
There we go. That's the contrapositive, right? So we do need that though. We still need the negation. We just do this backwards.
Yeah.
So it's not this implies not the hypothesis. So the contrapositive is if the integral is not equal to 0, like maybe it's 2 pi I, then f is either not continuous or it has no derivative. Then f is not continuous on G, or f has no derivative on G. So if the integral around a closed path somehow turns out to be non-zero, we know there's no derivative for that function on that region. So we know then that this equals 2 pi I tells us that this function has no derivative on any region containing a circle, a full circle. So this is why I know there's no antiderivative for 1 over z. The natural candidate here is natural log. but not on this domain. Not on the whole plane. Yeah. Is that a little, yeah, starting to pull things a little bit together.
Yeah.
Okay, so let's take a look here, and I think I've just said what I wanted to say. So when does an antiderivative exist? That's theorem 415. Theorem 415 is on page 78. We're just going to kind of read through this, but I might draw a little bit. So we have a region G and a fixed point Z naught in G. Listen, actually, I got to draw this stuff when I start looking at hypotheses. Even if the drawing doesn't do much.
Are
It's
you in
something.
the other version of the book again?
I'm on 154.
Our
Yeah.
page number is probably different.
Oh,
We have
yeah.
the same stuff.
Okay, cool. Okay.
My page number is 60.
Oh, how weird.
Oh, online, okay, I was
Online
like, it can't be the,
has
okay.
Online is a different page number.
That's bizarre.
They have like stuff, like the beginning and endings cut out, so that page number.
That's it. That's it. Yeah. So theorem 415, however you get there, we've got a region. That's G. We have got a fixed point Z naught in G. We've got a function f where G is its domain. That means f is defined on all of G. It maps into the complexes, and that is a continuous function such that the integral around on any gamma, for any gamma inside here, any closed path, gamma. Doesn't matter what orientation it is because it turns out to be zero. So gamma, integral over negative gamma would be zero as well for any gamma. Arbitrary path. If this happens for all gamma contained in C, then we're not violating that that conclusion over there. So we can't, that result isn't going to apply necessarily down there. So that's good news. And we needed to know that f was continuous as well. Then once we know that that integral is zero on any closed path in G, then the antiderivative exists. And we can create it. Then this function f from G to C defined by f of Z equals gamma of sub Z of f. So let's talk about this, and let's talk about Calc 1, because this probably looks a little weird, might be a little confusing, but you've seen this. What do I mean here? This is kind of like the fundamental theorem of calculus part. The other part you don't talk about as much in Calc 1. So this gamma is a path from gamma naught, that fixed, or Z naught, to a point Z. That's what the little sub gamma Z means there. So gamma looks like this. There's gamma of Z. And gamma Z can change as Z changes. So this integral here, what would this look like? Well, think about this. This little f has an antiderivative. Say big F. And we would take that big F and evaluate it at the endpoint. So it's Z naught to Z. So it's literally the antiderivative at Z. Same point right here. Remember, it doesn't matter what gamma looks like, how we got from here to here, minus the constant value, F of Z naught. So how is this related to Calc 1? Well, let's say in Calc 1, I've got this little function f of x is x squared. And I want to talk about its derivative, or excuse me, its antiderivative. Then I can create this function f of x, and let's actually call it f of z to make it kind of feel like that over there. It's going to be the integral from some place, x naught, up to z, of this function. I don't want to use, oh, I'll use x in there. dx, like this. So what does that represent? It's just the cumulative area. So if this is little f, oh well, no, I know what little f is. If that's little f, then this integral is everything from x naught up to z, and it's that cumulative area in there. If you take the derivative of this thing, so d dz of big F of z, it's d dz of this good old integral over here. And this right here is the fundamental theorem of calculus part 2, which says this is literally just x squared evaluated at z. So in other words, z squared. Now, there's another way to see this. Take this thing right here and work it through. So that's 1/3 x cubed evaluated from x equals x naught to x equals z. And that turns into 1/3 z cubed minus 1/3 a constant. This is like the plus c part that we're used to writing. Again though, notice that the integral, what's so interesting about this integral, when you did this in Calc 1, and your teacher may or may not have made a big deal about it, you can find the area under a curve, f, by just knowing the values of some function at the endpoints. So this whole idea of just worry about the endpoints is not new. This is actually Calc 1. That the area underneath here is totally determined by the value here and the value here of the antiderivative. So nothing mysterious, just looks way more mysterious because of the world we live in. See. Okay, I think that's all I wanted to say about 415. Now I want to talk about a new idea. Great word. Cool concept. I don't think we talk about this anywhere else. Let's talk about homotopy. Two curves. So here, let me give you the nutshell idea. A homotopy betwixt, that's right, two curves, gamma naught and gamma 1, on the same parameter space. Let's say they're all on parameter space 0 to 1. So they both have their parameters come from 0 to 1. If they don't, we could scale them to be that way. It doesn't matter. It's most important that they have the same parameter space. So a homotopy between two curves is, let's make two curves. Here's gamma naught. Here's gamma naught of A, or 0. Here's gamma naught of 1 here. And that clearly is the orientation, because here's t equals 0, here's t equals 1, and I flow that way. And then let's make gamma 1 different looking, maybe a little bit shorter, doesn't really matter. This is going to be gamma 1 of 1, and this is gamma 1 of 0. That's my flow. So I got these two curves in space, and they live in a region G. And the region is super important for the idea of homotopy. In fact, it kind of tells us something about the region, which we'll see in a minute. So a homotopy between this curve and this curve is just a formula that shows the user, the reader, how to transform each point here to a corresponding point over here in a one-to-one and onto fashion. So the homotopy is a way to continuously deform this curve into this curve. So a homotopy betwixt two curves, gamma naught and gamma 1, is a formula for continuous transformation from one curve to the other. That's all. And so it's the mathematical idea of this is made out of rubber, and I can flex it and move it all over. Or it's just a loose piece of string that I can reconfigure. Think of these curves as pieces of string. It's the way to move the string into the new form. Let's get a little bit more precise here. Let me get my notes because they're much more precise than my memory. So we've got this parameter space for each of these. So we're going to talk about the original parameter space. So there's the original parameter space. And that goes from 0 to 1. And then this axis represents the homotopy parameter space. And that's going to go from 0 to 1 for us. And the S is kind of like what slice of transformation we're taking right now. So in terms of our homotopy, we're going to start S equals 0 is this curve here. And S equals 1 is when I get to the other curve. And then S in between these is just what does the curve look like at that particular moment? So let's say here, right here, that's S equals S naught in that picture. So at this level, when S equals 0, this is my S axis here. When S equals 0, this is just the gamma naught curve. So this is parms for gamma naught. And by the time I've moved the other dial, so I've got two control dials. I've got a control dial on this slice, and I've got a control dial for moving up this way. Up here, once we get here, this is the parameters for gamma 1. And somewhere inside here, at say S equals S naught, are the maps to give me this curve right here. As I move T, then I move along that curve. So this right here is equal to midway curve parms. Let's call it parms. Bless you. So let's see, can we do a specific example? Well, they give a god-awful one in the book, but we can do something a little bit. So let me show you how they get their example in the book. So one of the things they show us is that a square of side length 6 centered at 0. So this is 3, this is 3i, negative 3, negative 3i down here. So I've got this square, let's call that gamma 1, and then we have a unit circled inside. So we'll call that gamma naught, and that's 1i, negative 1, negative. That's gamma naught. So you like this. Let me explain what you're going to see in that formula. And I highly recommend you look at it. It's pretty intense. It's on the couple pages forward. You'll see it, it's a piecewise thing. In fact, I'll put a part of it here so we can compare what we're seeing. So homotopy TS is equal to 1 minus S e to the 2 pi I t plus 3s times 1 plus 8it if t is between 0 and 1/8, and then a whole bunch of other shit I'm not going to write. Sydney concurs. Blah, 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 blah. So where did they get this from? How in the hell did they get this formula? Well, notice that this is a point on the circle. So e to the 2 pi I t is just a point here on the circle that corresponds to t radians. So there's e to the 2 pi I t. It's just this point right here. It's a very specific point on the circle. As t changes, we get all the points along the circle. So we start with that point, and we move out and figure out what point's out here. So let's see here. Here t is going up to 1/8. So that means this goes at most up to pi over 4 radians. You see that? 2 pi divided by 8 is pi over 4i. So that means this picture's a little off for that part of the parameter. That part of the parameterization is just this right here. And let me know if that doesn't make sense. So let's see here. So this is t radians, and then we got this point right over here. So notice, look at what happens as t goes from 0 to 1/8. When t equals 0, I'm at 1 times 3. It's actually, I'm going to pull this s out in front. I got this 3 like this. So when t equals 0, I'm at 1 times 3. I'm right here. As t moves to pi 1/8, then I'm at 1 plus 1i times 3, 3 plus 3i, which is this point right here. So this is the whole range here as t moves from 0 to 1/8. So we find that point over here. That's all we're doing. They're literally just taking the point that's over here, and that point is going to be 3 times 1 plus 8i over t. You gotta have the 3 in there. What are they doing then with this? What's the deal with this and that s? We've done this. They got a point here. Here's point 1. Here's point 2. What is this deal?
It's like moving in between the circle to the square.
Yeah, it's just that linear combination of the points between. We've done this, right? This is literally how we construct a line between 2 points, a parameterized version. So take your 1 point times 1 minus s, and your other point times s. Notice that when s is 0, I'm right here on the circle. When s is 1, I'm right here on the square. And when s is a half, I'm some combination of points in between. So all along here, we're just going to take s times the initial point plus 1 minus s times the final point. And that's the parameter for the transformation. That's this parameter here that shows you how to transform each point. And each point has its own path that we can decide or discern. So, it's pretty complicated looking, but when you break it down, it's nothing we haven't done. Interesting expression.
I feel like I understand it, but it's like, a lot's going on.
There is a lot going on. The key thing to remember is, can I continuously just deform one curve into the other? And a lot of times, most of the time, Labina, this is going to be mental. Let me give you an example of 2 curves that are not homotopic, but seem like they should be. The way to screw up a homotopy is to put a hole in the domain. So here are 2 curves that are not homotopic. 2 non-homotopic curves. Oh, by the way, I did put a new assignment up as well. It's up on World Class. It would be cool if we could do this if I could get it by next Wednesday. It's not crazy. But then again, I say that, I think I might have blown my credibility on that. But,
Well, now that you have the right book and Regis is in a more stable place, this should be fine.
yeah, it should be fine.
This is real wood, right?
So let's let G equal, our domain is the complex plane minus 0. Here's 2 curves. So let's let gamma naught of t be e to the it. Good old, doesn't that just seem lovely and simple these days? Good old circle, unit circle. And let's take gamma 1 to be 3 plus e to the it. So now remember, the domain of G and all the transformations have to take place in G. So that's 1, 2, 3, so I got this circle over here. Well, so that was pretty subpar. That's gamma 1, that's gamma naught. In your mind, so Labina, this is what I'm saying, like we can do a lot of this in our mind. Is there a homotopy in this plane, in this domain, that I can move this one into that one? And I can't, because I have to somehow move this thing through 0 somehow.
You can't split it.
I can't split it. It's a continuous, so let's talk about it. Homotopies are continuous deformations, which means no cutting, no tearing, no adding new holes, nothing like that. So preserving the original structure. So this thing, if it's closed loop here, it has to remain a closed loop throughout the homotopy. But at some point, to imagine one of these points going from here to there, one of these is gonna have to come through 0. At some point. So this thing can't be moved because it's got a hole in the center. You can think of these holes in the domain as poles that stick out, that you cannot move around. So remember that homotopy gets blown by holes in the domain. That's kind of what I really want us to understand right now. That changes everything. We're going to do some more practice with this. So now, finally, we are getting up to a big theorem. This is called Cauchy's theorem, so you know it's got to be big.
That man Cauchy.
He is the man. He's like seriously complex analysis dude, right? Like.
I think I've seen his name at least 25 times.
And yes,
Full
yes,
chapters.
100%. So let's take a look at theorem 418. I'm writing this up because it is a big one.
Most of Cauchy's stuff is.
Pretty much, yeah. He's like, I'm not putting my name on that. That's garbage.
No, we're gonna do that.
Yeah, why would I do that? I'm Cauchy. So we've got another region in C. I'm changing the hypotheses in a way, and I want you to tell me what the new hypothesis is. Gamma naught, gamma 1 are piecewise smooth, PWS paths. Not necessarily closed curves, paths. So they may not start and end in the same place in G. And gamma naught is homotopic to gamma 1 in G. So this symbol right here, this means there is a homotopy in the domain that we're concerned about from this curve to this curve. So let's write that out. Gamma naught is G homotopic to gamma 1. What that means is, i.e., there exists a homotopy from in G from gamma naught to gamma 1. Not stepping outside of G, I can continuously transform this one into that one. So I couldn't say that about those two curves. Not with that domain, G up there. This one, how about if I had one out here? This is homotopic to this, because it doesn't have the hole inside. This has the hole inside. These two are homotopic. That's cool. But the connectivity of the region is what this is all about. Or the puncturedness of it. So if I have two homotopic paths, then the integral over gamma naught of our function f is equal to an integral of f over gamma 1. Complex integrals are the same over homotopic paths.
That's tricky.
It is kind of tricky. So this is kind of an extension to This is kind of an extension from the path independence where it was just the endpoints, but this is even heavier. This is an even heavier result. Let's see, let's make sure I'm getting all the hypotheses up there. Yeah, that's good. It's much more vague. What is the difference here in the hypothesis? What changed all of a sudden? I gotta go pee. You tell me when I get back. I'll be right back. What changed in the hypothesis?
I nominate Levine as a villain. What was that? So you just got violent as soon as the professor left?
I'm very ticklish, so it's like one little thing and
I told Levine I'd hit her if she tickled me.
Wow.
Should I still you guys?
She asked me this morning if I was ticklish. And I told her I'd hit her if she tickled me.
That's a weird question to start out with.
It's Levina. I mean, a thumbs up. Oh my god. You're funny. I'm hungry. I got a hot pocket. I haven't warm up. I've been thinking about it since about 10.
Oh.
I got leftovers from Texas Steak.
Roadhouse?
Roadhouse.
Oh, do you have like the cinnamon butter?
No, but I have the
Oh.
rolls.
Dude, I love Roadhouse rolls. So
The
much.
TV show?
No, Roadhouse rolls.
Rolls, not
Rolls.
rules. Okay.
No. He was really confused. What the fuck are you
Huh.
talking about?
Yeah, we used to go there every year for me and my brother's birthday because we're twins. But then one year someone told them and he wouldn't get on the saddle and he made me do it alone.
Oh, I'm so sorry.
Yeah, it was traumatic.
I've only experienced that once. The saddle.
Yeah. See, but you're supposed to, when you're a twin, you're supposed to have someone to back you up. And he just
And
wasn't
you
there.
did, yeah.
I didn't
That's
know you
foul.
were a twin.
We're not identical. You wouldn't know if he walked in. You'd just be like, that's a.
Sounds like you're discussing this, but what's
Well,
different?
we were talking about like twins and stuff and identical, and in a roundabout way, you really,
Interesting.
you really could.
Humanitarian homotopies.
I was just gonna say that.
Humanitarian.
That's good. You were gonna say what about what's different? So does anybody? What is different? What have we been assuming in the previous hypotheses about integration?
They're continuous.
Continuous, yeah. The integram was continuous, and that what existed? Yes, the antiderivative. Yeah, so like every other theorem before was the thing I'm integrating is continuous, and there exists this wholly antiderivative thing up here, this primitive. Does this mention that? Which direction does this go in the hypothesis?
The other direction.
The other.
There has to, a derivative has to exist in 718.
Yeah, so check this out. This is saying for the integral result to hold true, all I need is to know that f is holomorphic in G. How do I check that something's holomorphic in G? What would I do? Cauchy-Riemann, right? So this is cake. This we've been doing. This is just like verify the Cauchy-Riemann equations hold in G, and then this holds true. Then the integral is the same on homotopic paths. Yeah? Okay. Cool. So we just got done with Cauchy's theorem. That's freaking awesome. Let's move to page 80. I don't know what page it is.
What theorem?
Yeah, well, yeah.
You'll figure it out. It's the next page.
Oh, sure.
No, it's actually 2 pages
Okay,
further.
we're lying now.
So look at the bottom. It says definition G contract.
Is that 2 full pages or 2 pages from?
2 full pages.
It's 63, I think.
63. That sounds reasonable. It's at the bottom.
Or 420.
Above corollary 420.
Yeah. I did not think we could not else to go.
All right. So the path G is a region in C.
Beautiful.
Yeah, sound good.
Yep.
If the closed path, so it's a closed path gamma, is G homotopic to a point, then gamma is G contractible. And we write gamma is homotopic with respect to G to 0. So what does this mean? This means something like this. I've got a circle, and I can contract it to a point continuously. So that's pretty easy. Just imagine that a series of diminishing circles, and you've got a homotopy to a point. This is assuming there's no hole in the middle. If I put a hole in the middle, all bets are off. Because I can't shrink to a point that's not there, and I can't shrink the circle, I can't pull it through a hole in the domain. So so this statement here, that I have a curve gamma that is G homotopic to 0, this essentially, for your purposes, means that there's no holes in G. That's what this means. There's no holes in G that are inside of gamma. So let's see here. Okay, here's G. Here's a hole in G. So I'm going to take a little hole out. I'm going to take another little hole out. The rest of this class is going to be a lot about these holes, for real. So here's a curve. Here's gamma naught. Here's gamma 1. Here's gamma 2. Here's gamma 3. I'm adding orientations, but it doesn't matter a whole lot. I'll just put them in their standard. And then here's gamma 4. Are any of these curves homotopic?
Yes.
Yes. Which ones?
Gamma naught, is that gamma 3?
Yeah, gamma 3. Yeah, these are homotopic. Yeah. Anything
Gamma
else?
1 and 4.
1 and 4 are homotopic. Gamma 2 is not homotopic to anybody else. Is anybody in here homotopic to 0, so contractible? Are any of these contractible? Yeah, so this one, I can shrink this one down to a point. I can shrink this one down to a point, but none of the rest. So that's how to understand what that means. So look at corollary 420, because I think somebody was mentioning it anyway. So we have these same hypotheses. We have a region G, we have a holomorphic function in G on a path that is G contractible. So there's no holes inside it. The integral around that path is 0. In complex analysis, the only thing that adds value to our integrals are holes in the domain. Places where the function blows up to infinity. These are going to be called poles for us in about a week. P-O-L-E-S. The poles of the function of places where it blows up, and they're the only places that accrue value for us, which is quite strange.
But they don't always accrue value.
It might be no, they always do.
No, we saw the squared one last week where it didn't accrue value because it was squared or something.
Right, okay, yes, that is true, yes. Yes. Corollary 422, if a function is entire, then its integral is 0 around any closed path. Makes sense, right? Holomorphic in the whole plane, make a closed loop. Every one of those is G contractible because there's no places where the function isn't defined. So the integral will be 0. Remember, I think I told you 2 pi I and 0 were like the main guesses? 0 is such a good guess. Lots of things are 0. Let's do a problem together.
Wait,
Yes.
Waiting.
so
Yes,
does
sir.
this mean that the derivative of 1 over z doesn't exist?
No. It means that the antiderivative does not.
Well, I can take the derivative.
Yes,
Okay.
absolutely. Yeah. Yes, because once you've said that, you've already taken 0 out, and so yeah.
And
the
all of
derivative-
these things are only over the complex plane and not extended complex
Correct.
plane.
Yes, sir. Yes.
Dang.
Let me show you how to do this, and this will actually, after today, you'll actually have enough to get that homework done, but it might take some talking. So let's say I want to do integral over gamma, which I'll give you in a minute, of dz over z squared plus 2iz. And gamma is the unit circle. So gamma equals circle around 0. of radius 1. I'm going to draw a picture because we might be interested in this picture soon. So there's 1, there's I. Any factoring that it can do here?
Z.
Right, so you got like that. So, see, yeah? Anything I can do with that? Could I break that into 2 fractions that add up to that fraction?
Yeah,
If you so desire.
but then like you
I do.
have to do that. Oh, okay.
What do you call the process of taking a fraction and decomposing it into a sum of fractions? We did this in DiffyQ. It's decomp. That's a good like safe word. Partial fractions. Method of partial fractions. So I'm going to take this, and this will become a friend of ours. Partial fractions again. It's cool how often it shows up. So this is equal to. I'm gonna just write this out. We're gonna wing this one through. I'm gonna show you how to kind of talk it through to yourself. Here's gonna be our 2 denominators, like so. Now think, you want a number up here and a number up here so that when you combine these together, the top becomes a 1. Right, so the top here is just a 1. So think about what it's gonna happen. To get these together, you're gonna multiply this one by this over itself, and you're gonna multiply this fraction by z over z to get the common denominator. So this thing up here is gonna become like bz, and this thing over here is gonna become az plus 2I. Do you see what I'm saying? I'm just kind of slopping this together. So like this bottom one's also gonna be multiplied by z plus 2I, and this one's gonna be multiplied by z over z. But what will the top become? It'll become az plus bz. And that's going to be a z thing. There's nothing z on top, so that I know that a and b have to be opposites of each other. These have to cancel, so there's no z's. And I know that a times 2I has to be my constant 1. This is not a good plan. I'll give you a good plan if you need like a refresher on how to do partial fractions. But today I just kind of want to wing this through. So a is going to be 1 over 2I. Z. And of course that's negative I halves, which we've seen before. And then b is the opposite of that. You can check me out on that. If you combine those 2 fractions together, you'll probably do it in your head now that you've seen it. You can kind of like spring them together. Okay, this is over gamma. So one of the other properties listed a little earlier says that this should be this integral over gamma plus this integral over gamma. And let's put minus 1 over. Okay. All right, we're almost done. So the amazing thing about complex integration is it's really not at all about antiderivatives in the end. It's about holes and knowing a few simple results. Remember this result. What was this? 2 pi I, right? That's a good result to remember. Because that's actually this integral right here, right? So this integral, notice that there is a hole inside of gamma, and so I do need some kind of work. I have to either work this through or know that result. Wait, somebody say something?
Sorry, I didn't realize you had defined gamma.
Oh, okay. Oh, sorry. I didn't write it clearly though. Oh yeah, I did. I guess, yeah, but it's easy to lose. So this is going to be 1 over 2I, and then we're just using that formula right now to call that 2 pi I. What about this integral? Where is the hole? Where does the integrand have a natural hole?
Negative 2I.
Negative 2I. So negative 2I, here's negative I, here's negative 2I. Is this path that we're integrating around, G contractible? If G is everything except that hole. It is, isn't it? Because that circle doesn't wrap around the hole.
No.
So I can shrink it to a point, so it's an integral over a point, and an integral over a point is 0. So this is because gamma is G contractible to 0.
Oh, so that second one is 0.
So this is 0. So the final answer is 1 over 2I times 2 pi I, and what is my final answer? I.
Wow.
Pi.
Isn't that fun? It's a whole new way of thinking. So partial fractions here becomes your powerhouse.
That is nice.
It is so cool. So the last problem on the homework set is just these. Good stuff, friends. Good stuff. Things are going to get so fun. So fun.
Whenever you start saying that, is when I start to worry.
We're getting too far a little bit.
This is going to suck.
Well, no, it's
You're
just,
going to hate this, Labina.
And they keep you at it.
it'll just be cool
At
results.
least in that form, she feels like he's being honest.